Hello. So today in this live session we'll discuss about electric charge and field chapter, and specially we'll discuss about dipole on the axis means electric field on the axis of the dipole, and we'll also calculate the net electric field on the equatorial plane. So let us wait for 2-3 minutes, then we'll start our discussion on electric charges and electric field. Okay, the sound and video is clear, I think. Let's wait for 2 minutes, then we'll start. Okay. So now we'll discuss about then up to this one I can write. The final one will be here, I think. Okay, so now let us begin our discussion. So we will discuss electric. We are discussing electric dipole today. And from every year the question comes from the electric dipole, that the net electric field on the axis of the dipole and on the equatorial plane. So if two charges, that is minus q plus q and minus are, let's say, separated by a distance 2a. Okay, if two charges, that is minus q and plus q, very small, it's not very large, the distance between the two charges is very small, and let's say the midpoint of this one, let's say it called center of the dipole. And remember that the direction of the dipole is from negative to positive, that is by convention, and we represent it with p cap. We represent with p cap. So this is your axis of the dipole. Okay, now we'll find out at a point P what is the net electric field. So before we calculate the net electric field here, I think all of you know the how to what is a net electric field, and or what is the expression for electric field. So if a charge q is here, in its surrounding there will be electric field. Okay, so at a distance r from the charge, the electric field strength will be, what will be the electric field? What is a net electric field? The electric field strength will be that E vector is equal to 1 upon 4 pi epsilon naught q upon r square r cap. R cap is the direction of the charge, direction of the field. Okay, so this is your electric field vector, and we also know from the electric field lines concept, for a positive charge the field lines are outward in nature. For a positive charge the field lines are outward in nature. Okay, and these field lines will electric field will use here. So for a negative charge the field lines will be inward, or you can say towards the charge. These are the field lines, and mathematically your electric field is 1 upon 4 pi epsilon naught q upon r square r cap, that we know. Now what we will calculate? We will calculate the electric field, net electric field at a point P due to a dipole, and this type of dipoles are, you can say, these situations create in molecules like polar molecules, like non-polar molecules like carbon dioxide or methane, CH4. So this type of molecules are non-polar in nature because all the electrons distributed in the surrounding of the nucleus in a symmetric way. That's why in case of polar molecules what happens? Now the electrons shift to one side and the nucleus, that is positive part, the shift side. So a very small distance between this electron cloud and the nucleus it created. And inside it, because atom as a whole is a neutral one, that's why the atom is the electron, that's why the number of or total amount of plus q, and this type of situation if it will arise, then it will create a dipole situation. Okay, dipole like situation. And polar molecules like H2O, okay, O and HH. Okay, so this is a non-polar. Here the electrons are not distributed in symmetric way. Electrons are distributed means shifted to one direction, and your proton or nucleus positive part atom is shifted to another direction. So there is a difference between electron and distance between electron total negative charge and the positive charge. There is a difference or a distance. So this type of situation, a dipole is created. Now we will calculate the net electric field at point P. So we will use the concept of these electric field lines and also this mathematical form of your field vector, electric field vector. So we will use both here in the derivation. So now let us calculate the electric field at point P. So electric field at point P will be the sum of two electric fields, that is the electric field due to plus Q charge, and as we have just discussed that for a positive charge the electric field is outward in nature. So the electric field will be in this direction due to plus Q. So I will write it, this is E plus Q vector, right. Now due to minus Q charge, the electric field vector is in this direction, minus Q will be towards, so this will be E minus Q, right. And your net electric field, so let us write, and one more thing we will discuss. So if it 2a and if the distance between plus Q and minus Q is 2a, so from center to the charge this will be, let us take the distance from the center of the dipole to the point P is r. Okay. So what will be the electric field E plus Q in this situation? E plus Q will be 1 by 4 pi epsilon naught Q by, what is the distance from here to plus Q charge? The total from here to here it is r, this is a, so from here to here it will be r minus a whole square, and of course the direction is this direction, that means it is in the direction of p cap, dipole, direction of the dipole. Okay, so you can write in that way. Now as you can, it will be 1 by 4 pi epsilon naught, and this is minus Q, that's why we will use once the negative sign, not twice. So I will write charge Q and the distance up to minus Q from P, this is r, this is a whole square, and direction is E plus Q, direction is opposite as the charge is a negative charge. So I will write minus P here, or I will write this minus symbol at the beginning. Now we will just add the two vectors, okay, and we will get the net electric field at the point P. That's what we are doing. Electric field at a point of dipole. So this is your axis, and on the axis of the dipole at any point P we are calculating the net electric field. Now we electric field at point P. So the net electric field at point P, that is E at point P, will be sum of these two electric field, that is E vectors. You can see 1 by 4 pi Q, these are common, so I can take the common out, that is Q by 4 pi epsilon naught, inside the bracket 1 upon r minus a whole square, right, minus 1 upon r plus a whole square p cap. P cap is the direction. Now just we will calculate some take L, just you will simplify and you will see what the result you are getting. So Q upon 4 pi epsilon naught, right? What will be the LCM? LCM is, you can see, minus R minus A square P cap. Now you see A plus B whole square minus A minus B whole square. What will be the result? A plus B whole square minus A minus B whole square. So what will be the result? Okay, so minus A minus B whole square is 4AB, that you know from your junior class mathematics. So you can write that this is 4RA, and A minus B whole square, A plus B whole square. So this whole square I can put another bracket and I can put a square. So this will be R square minus A square whole square P cap. Very small number, and square of a small number is again a very small number. So you can write that this, you can neglect this A square as compared to R square. So for R greater than A, we can write that Q by 4 pi epsilon naught 4 RA by R to the power 4 P cap R is Q. So the final result is your electric field at point P is Q upon, or you can write 1 by 4 pi epsilon naught. That one you can write K also, and 4 QA divided by RQ P cap. So this is your electric field at point P on the axis of the dipole. Now you can see the dipole, for a dipole the field strength is decreasing with 1 upon RQ, okay, but generally the field strength decreases 1 upon R square. So the field strength is decreasing faster in case of dipole than the single point charge, okay. Dipole means 1 upon RQ, okay. So here you can say so here is the expression for dipole, and you can express this electric field in terms of dipole moment vector. You can introduce a dipole moment vector, that P is 2 or Q 2A P cap, okay. So if you will reduce it, so it will be 2P vector, it will be 2P vector, and you can write this electric field at point P in terms of your dipole moment vector. So this question many times comes in the board exam, and you can practice these questions, okay. So tomorrow again I will come live in this time, and we will discuss about your electric field on an equatorial plane, and we will solve few questions, and also we will discuss about that if you will keep the electric field, keep the dipole inside a external electric field that is maybe uniform, maybe non-uniform, then what will happen, and electric flux, then Gauss law, application of Gauss law. We will discuss of electrostatic or electric charge and field chapter. Then in the next week in the revision classes we will start the capacitor and all these things, electric potential, chapter number 2, okay. Thank you.